Hello, and welcome to the circuits lab produced during the COVID-19 pandemic. And the point of this lab is to really give students some hands-on experience building circuits and comparing the properties of different circuits. The equipment we're going to use is, quite frankly, substandard. It's the best we could scrounge together to have enough that each student could really have their own set of equipment. But I hope you'll get something out of building these and just have a little more familiarity with how circuits come together and how potential changes as we move to different places in the circuit. The equipment you're going to have a multimeter, which in theory can measure potential differences between its two probes. It can also measure resistance between the two probes. And if you wire the two probes into a circuit, it should be able to measure current. That said, we're using a bunch of different meters, and several of them have been had their fuses blown over the years measuring current. So we are not going to attempt to do that in this lab. You're going to have a pack of resistors. These are probably older than I am, almost certainly, and they are definitely not at their rated values. So the first thing we're going to do is use our multimeter to check what their actual resistance is. We're going to have a power supply, which is going to be a AAA battery taped to a couple of alligator clips. And you may have to squeeze these a couple times to make sure you have a good connection. In this video, the first thing I'm going to do is just kind of show you a brief overview of how to use the equipment. I'm then going to say that students who are in class and able to do this, you guys should not watch the second part of the video. You should actually go out and try to complete this packet. If you're virtual or if you're in quarantine, I will then complete the packet so you can at least see sort of what the different things we can measure with this equipment is. So the first thing we're going to do is we're going to check our battery. It says it's a 1.5 volt battery. I'd like to see what the meter measures, kind of both as a check of the meter and also to see if that's accurate. We know that the battery probably has internal resistance, so this potential difference may not be accurate as we actually take our measurements, but I want to at least go through the process of measuring it. So most of the multimeters have a wheel in the middle, and you can use that to select different functions. What I'm going to do for my first one, I'm going to make sure it's set to DC volts, which is direct current, the kind of electricity that comes out of a battery. And this particular battery is 1.5 volts. So that means my maximum potential difference I'm going to measure is less than 2. So I'll set it to DC volts 2. I'm then going to hook up my probes to the alligator clips taped to the battery. Black is negative and red is positive. And the reason I'm measuring 0 is because this connection is not great, but you can see it then popped up to 1.588. You may have to just push them in to get a reading. So I'm going to record 1.588 as my measured potential difference. So you'll do that with yours. We'll then disconnect the battery entirely. We don't need this for the next part. We're going to go through and we're going to measure our different resistors. So if you look at a resistor, and this one is kind of brown, black, brown, and that's how we basically tell the difference between different resistors. And those color bands actually have some meaning, and I've given you what the rated numbers of these different ones should be. I'd like you to actually go through and measure those. So I'll do 1 here. We'll have to set this to measure resistance, and that's down here on this one with the little horseshoe for ohms. All of these are going to be less than 1,000 ohms. So I'm going to say on this particular one, I have it set for 2K, which means 2 kilo ohms. So this may be different on different meters. When it says 1 like that, that means infinite resistance. It's beyond the scale that we're measuring here. So you just touch both sides, do it on your paper, press really hard. Make sure all your connections are in. So I'm getting 209, really around 215 ohms. This is surprising to me because it's rated at 100 ohms, but like I said, this equipment is not the best. All right, 210 ohms, I guess. So I'll ask you guys to go through and get all of your measured resistances, and you can fill them in this table. All right, so I've gotten all of my values, and notice they're all pretty wildly off. And I've checked this with a couple meters just to see if this meter's wonky, and it just seems like these resistors are wildly off. So that's okay. What I gave you space in each of your data tables that you're going to use during the lab to do is to write what the actual values are. You'll just go through and fill all those out. And then on here, we'll just fill in what our actual measurements according to our equipment is. So you'll notice as you go through this packet that I ask you to build a series circuit, a parallel circuit, a combination circuit with one resistor that's not in parallel, and a combination circuit with two resistors that aren't in parallel. And the first step in each of these assignments is going to be to do some math and predict what you think the potential difference across all of your individual resistors ought to be. So I'm going to do that now for my series circuit. And I'll use this space down here to help. The first thing I think in a series circuit to do is to find my total resistance. And my total resistance is going to be 210 ohms plus 450 ohms plus 300 ohms plus 790 ohms, 1750 ohms. The next step, I think, is to calculate a total current for the circuit. So we'll use Ohm's law to do that. V equals IR. So 1.588 is I times 1750. So I expect a total current of 0.000907 amps. And you can see why we typically would use milliamps for currents this small. Easier for us though to leave it in the parent unit. Since this is a series circuit, there's only one place for current to travel, and that's through everybody. So it'll be the same current for all of them. So the next step is just to use Ohm's law, and basically they all have the same current. And you just sub in each individual resistor's values. So here it is for the 210 ohm. All right, so those are my predicted potential differences. And one good thing to check is in a series circuit, they really all should add up to the potential difference across the battery. So let's just check. 1.587. So that's what we predict. So what I'd like to do now is I'd like to actually build this circuit using what's called a breadboard. And we're going to actually see if these are the potential differences we get. Now, we're not going to be able to measure the currents because not all these meters have functional ability to measure current. But we'll go through and we'll basically just see what we get after we build the circuit. I'm going to copy my actual resistances down. I think we better talk about how do you build a circuit using a breadboard. So you can see on a breadboard, there's a bunch of holes, and there's some lines that go kind of across like this. There's a bunch of lines that kind of go vertically. And underneath the surface here, there are some connections. And you can see on this one, I've drawn a line through the holes that are actually connected under the board. So typically these things that are in a row of 5, they are connected under the board. And then these long rows on the top and bottom are connected as well. There's a gap, or there's several gaps on ours, and things are not connected across the gaps. So basically, I've connected these 2 resistors together by putting them both into this row of holes where they're connected under the board through the red line. So what does that look like for our series circuit? So it says take the 100 ohm resistor. I'm going to connect it like this. You do have to press kind of hard to get them in. Make sure they go all the way in. So there's that one and that one. So to my 100 ohm resistor, according to my schematic, I then need to connect the 450 ohm, which is this one. And I'll basically put the foot of that guy into the same row as the first one. So they're connected now in the breadboard. Then goes my 300 ohm resistor. And lastly goes my 790. All right, so there's my set of resistors. And now to complete the circuit, I'll hook the positive up to the 100. I'll hook the negative up to that guy. I'll squeeze those guys really tight to make sure it's connected well. And now I'm going to go around and check. So my potential across the first one is nothing. Squeeze those tight again. Make sure we have a potential difference. So the fact that I'm getting nothing means that my connection is not good. So you may have to squeeze the leads together on the battery while you're holding your 2 probes with one hand. It's a little bit of acrobatics, but it's fun. It looks like I'm getting 0.106 across the first resistor. And then across the second, 0.426. And across the third, 0.238. And across the last, 0.816. Disconnect your circuit when you're not using it so we don't drain the batteries. We'll see if these add up to the total voltage of the battery. If we look, they're pretty close to what we would expect to have here. There's definitely some experimental error, but hopefully that was kind of a nice introduction on how you measure the potentials across different items in a circuit. Let's just talk about how you build the other circuits. So you've seen what a series circuit looks like. Here's another way you could do a series circuit. This green wire and this foot are connected together. The resistor is kind of blocking the view. But you can see these two are in the same row. You could jump over one of those gaps in the breadboard if you want. Then those two are in the same row. And then back to your power supply. Check out this one. This one's actually a parallel circuit. The power is going in to this side of all three resistors. The other side are all connected together and the power is going out. This one's a combination circuit. The power is coming in. This resistor is in series with it. The electricity all goes through this resistor. Then it goes through the other two, and then it goes back out to the power supply. So what I'm going to have you guys do is build other circuits, namely a parallel, and then two different combination ones. And I'll ask all y'all to repeat the same measurements on those circuits. So at this point, if you are doing this lab in class, please stop watching this video. If you're one of the students doing it virtually and you want to follow along with me collecting the data, keep watching. So let's do the parallel one now. I think the first important thing to recognize that for parallel, everybody gets the full potential of the battery because these loops that we go from one side of the battery to the other, they all include just one resistor. So I'll give them all the 1.588 volts. So now calculating current, it's just going to be I equals V over R. So pretty straightforward for all of them. We'll go through and do that. All right, so we're not going to be able to actually measure these currents, but I would like to practice building the circuit and checking that we have the same potential across all the resistors. So building a parallel circuit, I guess what we'll do at first is I'll pull out all but one of the resistors. Maybe zoom us in a little bit here. So I'm going to move this guy up so that it's in the first row of two sets of holes. And I'm going to just basically put them all right next to each other, going into the same two sets of holes. And this is going to basically tie all of their feet together. Kind of starts looking like a spider at some point. And what each of these are just the separate loops that current can go through. And now we'll hook up the power supply to either side of them. Doesn't matter which foot we hook up since they're all tied together below. So there's my parallel circuit. So what we should see is all of them have the same potential across them. And of course, that's going to be challenging with me having to clamp down the battery, but that's how we roll in this lab. So anyway, full battery potential. Full battery potential across that first resistor. See if I can do another one. Yeah, I'm doing this last one now. Full battery potential. They all get the full battery potential. All right, so in this one resistor is not like the others. If we were going to draw the loops that current could go through that one, could go through that one, it could go through that one. This resistor has current passing through in all of the loops. So it's really in series with these others that are in parallel. So I think the first thing we ought to do is to simplify the circuit. So let's do this. So we'll leave our 390. We'll call this RP. And the resistance in parallel of it is 1 over RP is 1 over, oops, got to use the real values that we actually had. This is really 210 plus the 220 is really 300. And the 680 is really 790. And this one was actually 450. All right, so let's figure out what our parallel resistance is. So parentheses 1 divided by 210 plus parentheses 1 divided by 300 plus parentheses 1 divided by 790 parentheses equals, then we'll invert that. The parallel resistance is 106.83 ohms. Makes sense, it's less than all of them. We expect that as we open up more roads for cars to travel on, we expect the cars can travel more cars per second. So I expect a parallel resistance less than any actual resistor. I guess the next step in breaking this down would be we would make a circuit where everything was combined into a total resistance. So the total resistance would just be 450 plus 106.83. So 556.83 would be our total. So using Ohm's law, and since all current would pass through this imaginary resistor, and all current in this circuit would pass through the 450, we can find our total current. So V equals IR, 1.588 volts is I times 556.83. Don't want to get our unit in the way there. So the current is 0.00285 amps. So as we've seen, that's our predicted current through the 450 ohm resistor, which is really 390. Okay, what we can then do is we can figure out what the voltage drop across that resistor is, and then whatever's left over is what the parallel resistors will get. So just looking at this resistor, we expect the voltage drop to be 0.00285, and we'll use its actual resistance 450, at least according to our meter. So we expect 1.28 volts to drop across that resistor. So if we do Kirchhoff's loop rule now, we have 1.588 volts being put into the circuit, 1.28 dropping out there. Whatever's left over is the subtraction of them. So the parallel is going to be 1.588 volts, the battery voltage, minus 1.28 volts. So what we're left with is 0.305 volts for all of the other ones. Because they're all part of this parallel. And now as we go around this loop, up 1.5, down 1.3, down basically 0.3, and back to where we go. So delta V will be 0. So the last step in finding the currents would just be to do I equals V over R for all of these, and I won't make you watch all of them, but here's the calculation for the first. It would just be 0.305 over 210. All right, so here's all my my values. You can see that the bigger the resistor in parallel, the less current we got. So let's build this circuit and let's see if these potentials actually end up being close to what we got here. All right, so to build this circuit, we're going to start with our 390 ohm resistor, which is really the 450. And then what we'll do is we'll put the other 3 resistors so they're all hooked directly to it. This is a little bit tricky because you want them all to go into the same row of holes on both sides. Just take your time and double check yourself. And that looks good to me. So we want current to flow through the first one, then through the parallel ones, and then back to the power supply. So I'll hook positive the power supply up here, and I'll hook this back here. And once again, we won't be able to get the currents, but we will be able to get the potentials. So let's check. We'll have to squeeze our power supply because that's how we roll here. 1.37. And across the 100, which is really 210. Give our power supply a good squeeze. 0.214. And across our big guy here, also 0.214. Across that one, probably guess 0.214. So how do we do? Again, fairly close. We definitely have a much bigger voltage drop across the series resistor. And then we had all the ones in parallel with the same voltage drop. All right, one more. All right, so in this final circuit, if we look at our loops, we could go this way, or we could go this way. So the 220 and the 100 are in series with a couple of parallel ones, and we'll break it down in precisely the same way. We'll first combine these using the parallel rules, Then we'll combine them using the series rules. Since both of these guys get the full current, we'll calculate their voltage drops, and then we can use that to figure out the current through each of these branches. So I guess let's get started. The first step, I think, is to make this version of the circuit. So we have our 300 ohms and our 210 ohms. And then we have our equivalent resistance RP. 1 over RP is 1 over 450 plus 1 over 790. So 1 divided by 450 plus 1 divided by 790 equals invert 286.69 is RP. So now we'll combine those guys all together into a new total resistance. So our total is 300 plus 286.69 plus 210. So RT is 796.69. All right, so that's our total resistance. So what we can do now is we can calculate the current through this resistor, this imaginary one, and that will also be the current through both our series resistors. So if we go ahead and get it, we end up with 0.00199. So that's through our 300 and our 210. So we can calculate the voltage drops across each of them by just doing V equals IR. So for the 210, that means that what's left over for the two parallel resistors is the 1.588 minus 0.419 minus 0.597. Whatever's left goes to the parallel ones. So now we'll just get the currents for those guys. I'll do it for the 450. So 0.00127. So you could see significantly more preferred to go through the 450 than the 790. Again, there's more resistance in the 790. All right, final check. Let's build this circuit and see if we get something like it. So if we look, we go out of the battery and we first go through the 300 ohm one, which is the one labeled as 220. Then we go through the two parallel ones, the one labeled 390 and the one labeled 680. So we'll go into that one, and then we'll put our parallel route. So this one feeds into both of these, and then they come back to the same place. And then we finish with our smaller resistor. So that should be our circuit. And let's see what we get. All right, so we predicted across the first resistor, which is the 300 ohm one, we predicted 0.597. So we'll get those guys touching and squeeze my power supply. 0.604. For my other series resistor, we predicted 0.419. I'm getting 0.27 for that. So the potential difference across these two guys, .710. So that's off enough that I really wanted to investigate what was going on. And the one that clearly is the most different is we expected to have a voltage drop across the 210 ohm resistor of about half a volt, 0.419. And we got much less than that. And all of that went into the two parallel resistors. So my first thought was, are one of these parallel resistors not connected? Could that have been the issue? But I checked them, they both were. And I really have been racking my brains as to what's going on. Remember that the 210 ohm resistor is supposed to be 100 ohms. So after a day of experimenting with circuits, I decided I would check the resistance again. Instead of being 210, it's back to 100. So I don't really have an explanation for that. I don't know if there were chemical changes that occurred over time to this resistor, or there were oxides that wore off after all of this use. I think that's probably the most likely scenario. I'm happy that the rules of physics didn't get broken here. But if I was going to write a conclusion for this lab, I would definitely be talking about sources of error, using old materials that maybe the outsides have had oxides form on them, and that's increasing the resistance. I hope this walkthrough is kind of giving you some experience doing electronics labs. I would love to be doing this more in person, but I wanted you to have at least some taste of what it's like to actually do it.